Uh, Welcome to our next colloquium talk. Today's speaker is Kadri İlker Berktav, who got his PhD from Middle East Technical University in 2021. And then he worked as a postdoc in several institutions. One of them is University of Zurich, right? And the other one is Istanbul University.
Technical one.
Istanbul Technical University. And now he is working as a visiting assistant professor at Bilkent University. Today he is going to talk about derived algebraic geometry.
Okay, thank you for the introduction and having me here. It's always a pleasure to be part of this event. Yeah, today the topic is derived algebraic geometry, but as you may guess, I don't know why I choose this topic, but this is a kind of a tricky topic. It's a little bit involved framework, but of course in this talk, without any technicalities, I mean, no technicalities will be given. I will just discuss basic ideas. I mean, if you don't understand anything, I mean, it's not a big deal. I mean, the only thing you should focus on is try to understand the mind setting. I mean, why we need such a framework, why, in what sense derived algebraic geometry is useful. I don't know. So we will discuss what kind of framework we have, try to understand the basics, why we care, you know, do we really need it? Or I don't know. So I will basically discuss some terminologies, hot topics in this, you know, derived community. So let me start. So very roughly speaking, so there is a short way of encoding derived algebraic geometry. So the derived algebraic geometry, for short, DAG, is just is combining ideas from different mathematical domains. Okay, so especially it combines ordinary algebraic geometry with homotopy theory. Okay, homotopy theory. Of course, while doing this, it uses actually the language of infinite categories. Okay, infinite categories. So so of course you may say, okay, I have no idea what is algebraic geometry or homotopy theory. I mean, the same logic. It's not a big deal in this talk. So they are rich and powerful theories. But in this talk, actually, you don't need to know exactly what they are, but we try to understand what kind of, you know, framework we have. Okay. So so very roughly speaking, this derived algebraic geometry sometimes can be considered as a higher categorical. So let me write it down. Higher categorical or homotopical refinement of the ordinary algebraic geometry. Okay, so somehow you want to do homotopy theory in the context of algebraic geometry. Okay, very roughly speaking. So in this talk, we will discuss the basic ideas. So our plan, so after this short introduction, our plan is, so in the first part of the talk, I will discuss some motivations. Okay, motivation. I mean, historically, I mean, why people, you know, try to approach certain problems by using this language. And secondly, I will just discuss some terminology. Terminology. Okay, I couldn't. Okay, you understand. And finally, we will discuss some directions. Okay, so what kind of topics people are interested in. Okay, so I mean, this will be some biased list, but I will just mention some directions. Okay, what people do essentially in this framework. So let us start. So briefly, let me just mention some key ideas before the actual motivation. So key ideas. Okay. So the long story short, I mean, as I said, the first one is, this is a kind of this is the first one, higher categorical or homotopical refinement of the ordinary algebraic geometry. And because of this, it actually offers, okay, let me say, a new way of organizing the data. Okay, so the new way of organizing the data. Okay, I mean, for instance, why this is useful. For instance, if you are interested in moduli theory, so I'm just trying to tell you some keywords, okay? So without any technical details. So moduli theory, for instance, moduli theory. Actually, we will discuss more. Or the intersection theory. Okay, intersection theory, or even in physics. Okay, in physics. So ideas coming from derived algebraic geometry, or the way of, organizing the data, turns out to be, very useful in these domains, in these mathematical domains. And there are many other examples, of course. So I'm just briefly mention some of those. What else? For instance, the key problems actually where derived algebraic geometry arises, essentially, let me write it down. It provides a new setup to deal with non-generic situations. Okay, provides a new setup to deal with. Okay, to deal with non-generic situations in geometry. Okay, so what does it mean? Typical examples are intersections, actually, we already mentioned, the bad intersections and bad quotients. Okay, so these are two important problems that we will mention more. So let me just say bad intersections, whatever it means, and bad quotients. Okay, so we will discuss more. And finally, another key ideas, at least you should remember at the end of this talk, this derived algebraic geometry framework also offers generalized geometric structures. Okay, generalized geometric structures. Okay, so what does it mean? For instance, maybe some of you know already, recall, there are very nice geometric structures, right, on a manifold, in a differential geometry, algebraic geometry. So classically, on a smooth manifold, I mean, if you don't know what the manifold is, not a big deal right now. It's some kind of a nice space. In general, these are some building blocks for geometry. There are interesting geometric structures. There are geometric structures. So just some keywords. Riemannian structure, for instance, or symplectic, or maybe Poisson structure, complex structure. I don't know. What else? Contact structure, and many others. Okay, it's a very well-defined theory. Individually, each case, Riemannian geometry has many interesting results, concepts. So these are all different words and different mathematical domains. And this derived algebraic geometry, to some sense, generalize these things. Okay, so the question is, what if our underlying space is not a manifold? Okay, it's something highly singular, for instance. So what if, so the question is, what if the underlying space is something highly singular? Okay, you forget manifold structure, you forget smoothness, everything. So can we discuss symplectic geometry? Okay, I mean, is this reasonable? Is there any reasonable framework in which we can generalize this smooth setup? Okay, this is the main idea. Okay, let's go back our actual motivation. So the motivation part. So as I told you, so the bad intersection and bad quotients are the actual motivations. I mean, in some sense. Let us quickly recall intersection theory. Okay, intersection theory. It's a very typical in algebraic geometry. There are nice methods to deal with intersections. Okay, for instance, if you are familiar with, there is this old and nice Bezout theorem, right? Let me just 1 minute. Okay. Bezout theorem. So in algebraic geometry, if you have a plane curves intersecting transversally, and there are other assumptions, but very roughly speaking, let's say you have plane curves like this and like that. Oh my, it's a bad picture. You cannot apply even Bezout theorem in this case. Okay, let me just sketch something like this. Okay, as you see, there are some intersection points, and you want to understand the number of intersection points. Okay, let's say these are some curves. Let's say this is the curve C, and this is the curve C prime. And if they meet transversally, let's say, so these are some plane curves. Okay, and there are other assumptions, but I'll just skip that part. Meeting transversely, it means that it's kind of a very expected intersection. So transversally means you really expect to see something like this, really an expected intersection. Okay, this is the expected one and accepted one. So what does it mean? Maybe I can just a simple example. Just consider the parabola, right? Y equals x squared, and some line intersecting this parabola, right? Okay, this is line, I don't know, with slope x, let's say +1. Okay, something like this, or maybe this is wrong, so you can pick something else, but you understand the picture. And you don't want something like this, some tangential intersection like that. Okay, we don't want this. Or overlapping, so these two curves exactly coincide to each other. We don't want this. Okay, so we really want to see some cross like this, very roughly speaking. So this is called transverse. If this is the case, you can see that this intersection has exactly degree f times degree g points. Okay, which is perfect. So as you see, this is exactly 2 times 1. Degree 2, degree 1, 2 times 1, 2 points, as you see in this example. Okay, very simple, so very nice. Even, I mean, proving this theorem is requires some algebra, as maybe you know. But sometimes, if you forget transversality, okay, this theorem is not enough. I mean, you miscount the intersection number. Okay, so in this case, we need to use another machinery, okay, which is called the scheme theoretical intersection. Okay, so it is, I mean, at this stage, it's really, I mean, I'm not going to define what kind of intersection we have. It requires some algebra and there are some technical details. But the best thing about this intersection, it actually deal with non-transversal case. Okay, so it actually solve non-transversal case as well. But be careful, still for curves, okay, curves. And then, but the problem is, this is very nice, very good, it's a very important place where the scheme theoretic formulation of algebraic geometry is very useful, but not enough. But still, fails in higher dimensions. Okay, which means that if you have some higher dimensional varieties, and if you want to count the intersection number, and if you use scheme theoretic intersection, it fails. Okay, it gives you the wrong number essentially. I mean, there are other notions: intersection multiplicity, intersection number. So there are some technicalities, but this is the rough idea. So another approach, finally, the SER formula. It's a very important formula. SER's formula, it essentially, so it's really, I mean, at this stage, it's impossible to describe the SER formula here, but very roughly speaking, it means it essentially combines scheme theoretic intersection number as above, and it adds a correction terms plus correction terms, or sometimes it is called a higher higher terms. And this formula, whatever it is, this is the idea behind this formula. This gives you the correct number, gives the correct intersection number. Good. So you understand the general approach, so the general mind setting. So somehow you want to combine different ideas and tools, and actually these are coming from different mathematical domains. For instance, in SER formula, you need to use some kind of homological and commutative algebra tricks and constructions. In scheme theoretical intersection, you need to use local rings and everything. So there are details, but you understand the mindset. Sometimes your tools are not enough, so therefore you need to, in some sense, upgrade them. But the best thing about this SER formula, we need to mention, this is exactly the first place where the notion of derived intersection comes into the picture. Okay, this essentially leads the so-called the notion of derived intersection. Okay, back in that time, of course, people didn't call it derived intersection, but nowadays we call this formula as a very primitive and prototype construction of the so-called derived intersection construction. Okay, as I said, whatever it is, I'm just give you possible keywords, some directions, and everything without discussing too much technicalities. Anyway, so this is intersection theory part. The other part is quotient space. Okay, quotient spaces. Okay, good. So quotient spaces, what are those things? Actually, let me just give you a motivation. These are very useful things, useful objects, okay, in the context of moduli theory. Okay, for instance, in moduli theory or moduli problems. Okay, of course, you may say, okay, we have no idea about those things, moduli theory and moduli problems. The basic idea is, so mathematicians essentially wants to classify things, right? Because we are lazy, so we want to understand some equivalence classes, right? So this is really about classification problem. Classification problem. Okay, you want to classify things. So if you want some example, vector bundles, or the basic, very easy example, finite dimensional vector spaces. Okay, if you have an n-dimensional vector space, it's easy, right? Every vector space, finite dimensional vector spaces, are nothing but Rn, right? We know that, therefore, for any positive integer, you have a vector space, right? Easy. So there is nothing interesting about vector spaces. I mean, they are all isomorph, up to isomorphism, of course. So classification up to something. Okay. So the best example is this, for instance, positive integers essentially classifies classifies finite dimensional. We have some base field K vector spaces, right? For each n, you have Rn. This is your model, actually. Anyway, there are some details up to isomorphism, right? So you want to classify things, essentially. There are other, of course, advanced examples. If you are interested in algebraic geometry, moduli space of elliptic curves, moduli space of algebraic curves, I don't know, moduli space of vector bundles, sheaves, everything. So okay, there are many other advanced examples, but this is the mind setting. Okay, so you want to find some space like Z here, so that each element defines the object you want to classify up to something, up to some equivalence. Okay, so therefore, naturally, you need to use quotient spaces. Okay, this is the idea. Very good. So let me just give you another natural example. I mean, if you are familiar with group actions, for instance, you may have a manifold, some space, and you have some group. Okay, let's say this is a group, and this is, for instance, a manifold. And you can define action, right? Group action. So how to define these things? So it's kind of a map satisfying some axioms, right? Very roughly speaking, you have GP, and this gives you, for instance, let me denote this action by triangle, G triangle P. Okay, this could be, for instance, a rotation. You may have P. Once you act by G, P might be rotated over here. Okay, oops, let me just call it Q. So Q is some G left action P. So there are left actions, right actions, or whatever. Okay, so therefore, you can define an equivalence relation by using this action. Define an equivalence relation like this. 2 points are the same. This is the way of defining sameness, which will be important later. Equivalent if there exists G in G such that Q is the image of P under the action of G. Right? Something like this. So you can define a space by using this equivalence relation, and which is exactly M over G. Sometimes we use this notation. So far, so good. But what is the problem here? Actually, there is a problem. So you have a natural map, right? So you have a natural projection, right? For each P, it assigns the equivalence class. Okay, this is a set of equivalence classes, or let me just say the collection of equivalence classes. The question is, you start with a manifold, right? Did you lose any information after this quotienting out operation? So this is the question. So is M over G a manifold? Okay, do we have a structure of a manifold? The answer is no in general. Okay, and in general, in a very typical case, it is just a set, nothing else. You don't have any other structure. Actually, you lost information. You start the structure of a manifold, and then you lost this information throughout this quotienting out operation. And this is a problem. Okay, so this is not a manifold, as I said. Mostly, if you are lucky, this turns out to be a manifold, but mostly this is just a set, which means that we lost information during this process. This is not actually we want, right? We want to preserve the structure. But of course, the question is, do we have any condition, right? Can we impose so that we obtain the structure of a manifold? Yes, actually. So it is possible. It is possible. There is a sufficient condition if G acts nicely. Okay. Black box. whatever it means nicely. For those, I mean, who are interested in those things, the action, if your action is free, then the resulting object turns out to be a manifold. But it's just a sufficient condition. But let us formulate this problem categorically. So using categorical terms, it means that your category is not good enough. Okay, it means that the resulting object, which is in this case M over G, may not live in the same category. I mean, in the same category you are started with. You start with a manifold, which means that you pick some object from category of smooth manifolds, but the resulting object after this operation, it fails, you know, to be an object of the original category. But still, there is a good news, but still it may be a well-defined object in somewhere else. Okay, in somewhere else. But what does it mean? It means that your category is not good. We discussed this before, but maybe the notion of category is not enough. Okay, so sometimes some categories may not be that much good. Technically, if they admit colimits and limits, whatever, there are some technicalities, the resulting object will live in the same category, but sometimes some categories do not have enough structure, enough property, and therefore operations like this gives you some object which fails to be in the original category. Okay, this is a problem. But maybe the real problem is you shouldn't work with categories. Okay, so therefore the possible answer, maybe you need something more. Maybe you need higher categories. And spaces which can be interpreted meaningfully in the context of higher categories, which are called higher spaces. Okay, maybe the resulting object is not a manifold, but something else which can be defined algebraically in the category of something. Okay, so let me just give you some terminology. In general, if you ask this higher category people or community, the general terminology is when we say, for instance, spaces, we generally mean ordinary spaces, okay? Like topological spaces, manifolds, I don't know, varieties from algebraic geometry, or the general version of varieties, schemes in algebraic geometry. So any kind of standard spaces or vector spaces, I don't know, we just call them spaces. And when we say higher spaces, we mean most of the time stacks. Okay, or depending on what we are doing, these are maybe higher stacks or derived stacks, or higher derived stacks or schemes, which are just the generalized version of the spaces. Okay, and we want to interpret these spaces as a part of some kind of infinite categorical context. Okay, so therefore, if you go back our example, if you look at the literature, the idea is instead of naive quotient, quotient space M over G, Okay, we use or we consider M over G as orbifold. We use this, which are just called orbifold. We use orbifolds or more generally stacks. Okay, so for instance, if you have a moduli problem, maybe your moduli space, even if you are classifying manifolds, your moduli space may not be a manifold, but it could be just an orbifold stack or something else. Okay, these are some key ideas. Of course, the problem is, I mean, the price you should pay. I mean, this is nice. It's really easy to say. It seems very easy to explain. But the problem is, depending on what you want, each step requires different level of abstraction. Okay, different level of abstraction. So therefore, if we combine these problems, bad quotient, so conclusion. Okay, let's combine 1 and 2. A general conclusion is we need a new setup. Okay, we need a new setup. Okay, extending or enlarging ordinary categories. Okay, ordinary. I mean, as I said, it depends on your problem. Maybe you don't need that much level of abstraction, but maybe sometimes you need to pass the 2 categorical level. You don't need to go higher. It depends. We will discuss. And so you have a new setup, so that, okay, the resulting object, under this quotienting out operation or intersection process, or it depends on your problem, will actually lie in the same place. Let me just say, will lie in the same place. But what is this place? This is a huge question mark. Maybe this is just a 2 category, maybe infinite category of something. So therefore, we just want to extend our classical framework. And so we just extend the classical setup in derived and sticky directions. So this is the main idea. Okay. And this essentially leads to derived algebraic geometry. Okay, this is essentially the context of derived algebraic geometry. Of course, I'm not telling you how to do this. I mean, this is too technical, but this is the motivation. Okay. But some keywords, or sometimes this is called homotopical algebraic geometry. I mean, if you are interested in, let me just tell you some keywords. For instance, model categories. I mean, for this extending procedure, you need to use model categories. Actually, this structure allows us to do or define homotopy theory abstractly. Okay, this structure actually gives us in an abstract way and explain us how to do homotopy theory. So this structure, abstract way of doing homotopy theory. This is where the name comes from. Okay, so the model structure, you need a model structure on your category, and then this gives you derived categories, and this gives you somehow infinite categories. So these are some necessary structures, necessary framework you need to to deal with successfully this extension. Okay, you need more dictionary, more tools actually. And then derived schemes and stacks are the corresponding spaces. Okay, this is the idea. Or there are derived manifolds if you are interested in derived differential geometry. There is this notion of a derived manifold, but in each step you need some kind of new dictionary or new tools and approaches. Okay, this is the motivation part. Let's discuss briefly how to discuss these higher spaces. Of course, it's the technical definition, but there is a core principle. So let me give you the key idea. So how to define higher spaces. What is the basic logic? Okay. In general, people use functorial approach. Okay. Here, the essential idea is you can view higher spaces as functors. Okay? This is the reason categorical dictionary come in handy. So view higher spaces as certain functors. Okay, you need the language of category theory, functors and everything. So this is the point. I mean, why? This is the reason why people nowadays try to adopt this, try to learn and adopt categorical language, because this is, I mean, if you are interested in these things, these are everywhere and inevitable. So if you try to, understand these things, and this is possible for those who likes technicalities. This is possible by using Yoneda famous Yoneda. Okay, what was it? Yoneda lemma. Okay, this is a very important conclusion coming from Yoneda lemma. So you can even manifold. So you can see manifold as a certain functor, because there is a nice embedding from spaces to space of functors. Okay, so this is the idea. So you can even embed the notion of a manifold inside the category of functors. So you can see manifold as a functor as well. Okay, so this is called functorial, I don't know, point of view. Okay, functorial point of view. Good. So let me just briefly show you, just for future reference. For instance, in algebraic geometry, forget derived stuff, there are schemes, right? So schemes are the central objects. So schemes in algebraic geometry, you can actually view schemes as a functor, okay, from category of commutative K-algebras. So for instance, if you pick some object here, this is just a commutative K-algebra. So what is the basic idea behind this, theory of algebraic geometry? This guy, this A, essentially plays the role of C infinity n in manifold theory, right? So this corresponds to your algebra of function, essentially. Algebra of functions. Okay, so the basic principle of, I don't know, the Grothernik view of algebraic geometry is just, if you understand the algebra of functions, you understand the space itself. Okay, this is the basic logic behind algebraic geometry. Okay, this is the Grothernik point of view, or maybe a little bit older. Anyways, and the target category is sets, essentially. But of course, this is just an ordinary space. For higher spaces, you need to play with source and target categories. For instance, instead of sets, you pass to something, okay? This is the category of groupoids, but this is already two categorical level. This is the two category of groupoids. Whatever it is, okay? This is not that much important right now. The important part is the first level is just the one category level. This is the one categorical object, which means that the standard category theory, encoding the situation. But now, if you pass here, this is like your two functor. This is just your functor. I mean, if you want more technical terms, these are just sheaves, if you are familiar with these notions. So these are actually sheaves. But if you have no idea, it's not a big deal, some kind of map, if you wish. And then you can keep playing the same game. Instead of groupoids, you move to simplicial sets. But now I need to tell you what's going on. Okay? I need to tell you what's going on. On the right-hand side, what you are doing is essentially, so let me write it down here. So when you move from top to bottom, what you are doing is actually introducing higher morphisms. Okay? So there exists more higher maps. Actually, it is like maps between maps. Okay? For instance, this two categorical level, you allow maps between maps. And if you move towards simplicial sets, and I will explain why I use this familiar notion of simplicial set, you now have infinite tower of equivalences. Now you can obtain infinite tower of equivalences, maps between maps, between maps, between maps. Remember the moduli theory. You define, for instance, vector bundles up to something. You define vector spaces up to linear isomorphisms. What if linear isomorphisms are up to something, up to higher map? Okay, this is very easy to think if you consider simplicial sets from topology. The idea is you will see, for instance, you have points like that. Okay. So you have pair of points and you ask when, so this is your question, you have AB. So AB are just your zero simplex. Okay, just point or vertices. Okay, when AB are equivalent, you ask this question, right? And you may say if there exists path between them. If there exists a path between them. If there exists a path between them. Right? And let's keep asking. When, because there is no reason this path is unique, right? You may have other paths like this, G, and you may ask when two paths are equivalent. Okay? When FG are equivalent. You may say if there exists, if you are familiar with this topology, if there exists homotopy between them. Right? Something like this. We are done. This is topology. Okay, there is no higher structures, but you can keep asking when two homotopies are equivalent. Okay? So keep asking when, for instance, you may have other homotopy like this. Okay, let's say this is F, this is G, and this is phi prime. The question is when phi and phi prime are equivalent. Okay, and you may say if there is a higher map, if there is a homotopy between homotopy, maps between maps. Okay, can you follow the logic? So therefore, if there exists some psi, okay, joining these two. Good. And of course, you can keep doing the same thing. This is the reason why you have infinite categories. You can ask when two psi's or psi prime, right, equal to each other, blah, blah, blah. Then you need higher maps. But the best thing is, remember this analogy here. Let's go back. So the zero simplex is your object in your category. One simplex, these are just, one cell. So you are kind of attaching one cells, joining 2 points. And then you are attaching 2 cell here, phi. Phi is your 2 cell, bounding F and G. And then you are attaching psi. It's 3 cell inside everything. So you have one simplex. These are your morphisms. And then you have 2 simplex. This is your higher morphism, 2 morphism. And then you have 3 simplex. Then it gives you 3 morphism, in this case, psi. These are phi and phi prime, and these are F and G. And the story goes like this. Objects are A, B. And we want to keep this process infinitely. This is how or why infinite categories enters the picture naturally. Infinite category theory gives you such a flexibility. Okay? So infinite cats needed to encode this situation. Good. So this is very important. So this maps up to maps gives you the sense of sameness, how to define 2 objects are the same. And this is the most general case. Okay. Actually, we are almost done. So I'm not go back the left-hand side. Here, the right, let me just complete this picture. So this kind of assignment will be called higher stacks. This part is just stacks. This is the reason once you have it stacks, which means that you have enough structure to encode higher maps. Okay. When you have higher stacks, you have enough structure to encode, I don't know, higher maps. Okay. Maps between maps, everything. But there is a left-hand side, because I didn't tell you what this drive thing is. There is let me just leave it like this. So there is some gap here, and there will be something here and some assignment here, which we will call drive stack. But at this stage, I'm just going to skip that part. But you understand the main logic. So you want some structure, you want something more. Therefore, you need to change your framework. Okay, this is the general idea. So let me just end the discussion, okay, the presentation, by just introducing some hot topics. Okay, hot topics. What people do. What people do in drive algebraic or neighboring topics. Of course, it will be just some kind of biased and non-complete list. At least the topics are, let me just write it down, I am interested in. It's a biased list. I think the very hot topic is drive symplectic geometry. Symplectic geometry is a very interesting area. Actually, the basic idea is you can define, you can define the notion called shifted symplectics. These are just advanced remarks. If you don't understand anything, it's not a big deal. These are some advanced remarks for I don't know, for those who might be interested in. So define shifted symplectic structure on drive stacks. Remember the fancy objects encoding all higher relations and everything? Right? And the best thing is, remember, for symplectic geometry, you need an underlying smooth manifold structure. Now we forget this manifold structure And this guy generalizes the classical setup as well. I mean, this is not something, you know, disjoint, but this is really extending the ordinary symplectic structure on manifolds. Okay, and ordinary in sense that all classical picture sits inside zero shifted level. Sits inside zero shifted level. Okay, whatever it means. But of course, the problem is classical results in symplectic geometry, I don't know, happen to be very complicated, very hard to prove in the derived context because of the flexibility and higher relation and everything. But still, there are very nice results in derived symplectic geometry. For instance, I don't know, forget the for instance part, so it's a kind of advanced remarks, but if you are curious, then maybe we can discuss more later. But I don't know, classical results like Darboux theorem, Lagrangian neighborhood theorem, so these are just advanced remarks, are also valid in this derived context, or can be extended to that level. Let me just tell you that much. So the other thing is derived Poisson geometry. Okay, so if you have a symplectic geometry, it's natural to, you know, discuss Poisson geometry and also deformation theory. I don't know. So the main motivation of this program is actually kind of quantization problem. Okay, so therefore, let me just say, I don't know, what should I say? Physics sides. For instance, you can discuss derived geometric or sticky formulations for gauge theories. Okay, or another subject, functorial field theories. I don't know, topological quantum field theories. I'm just, you know, stating bunch of maybe abstract nonsense right now, but these are very rigorous and nice results. I mean, if you don't understand, it's not a big deal. I'm just tell you some keywords. And then deformation quantization is another important I don't know, area here. Algebraic quantum field theory. This is also very interesting. I don't know, there is this derived differential geometry. Derived differential geometry. I don't know. And there are maybe other examples in which I'm not that much, I'm not the right person to ask those things. So number theoretical side, foundational parts, logic and everything. But regarding geometry and topology, I guess these are very important and hot and ongoing subjects. Yeah, so there are other mathematical domains where you can see derived or higher categorical, you know, formulations, approaches to deal with certain problems. But this is not just a language, so you need to be careful. Maybe as a last remark, so this is a new dictionary, but at the same time, it's very useful to solve very, you know, long-term standing problems in mathematics. Okay, this approach is very useful, but of course, it's really sometimes hard to learn. Maybe it's really, you know, get used to the language, dictionary, and everything. What is new? What is just a change of formulation? But of course, in mathematics, sometimes you need new formulations with new tools, new algebra, so that you can attack, you know, the current problems with these new approaches. This is more or less the idea of this talk. So I try to give you an overview of this theory, and I guess this is more or less the story. Okay, maybe I should stop right now. So thank you for your attention.